Guys, hello everyone and welcome to the channel. So we have done first part of inorganic NMR spectroscopy and you guys have given good response to that, so thank you so much for that. First of all, second thing is that I know that there is a big gap between first part and the second part, and I will try to make sure that the next part comes as soon as possible. So I'm planning to make this series videos twice a week so that it can be finished as soon as possible, and you get all the benefit of it before the next CSNet exam, right? So that's what is one thing which I want to make it clear. So in the previous video we have discussed about how the splitting happens and how you find out similar types of groups in the same molecule, right? Let's say if you are finding out proton NMR, so how many types of hydrogens are there? Then if you are finding out phosphorus NMR, then how many same types of phosphorus are there in the same molecule? So we have tried to do that in the previous video and we have done that part. We have also discussed over there that how it is going to split out based upon their I values. Now here in this video I'm going to just extend that a little bit. I'm going to talk about that how that splitting, the splitting of the peak is going to caused because of the neighboring groups, okay? And that's what we are going to talk about. We are going to talk about majorly about J coupling in this particular video, okay? So about J coupling, how we will do questions related to it. Also we will try to understand all the other exceptional cases which we have regarding J coupling. So in case if you have never studied about J coupling in inorganic NMR spectroscopy, then this is the video which you should watch completely and understand the concept. It's super simple, it's very easy. Just hold on with me and watch the video till end, okay? Also it would be very beneficial for you if you will keep making short notes with these particular videos. All right, now having said that, let's continue with our video. Let's talk about J coupling. It has various different definitions. It depends upon at what perspective you are studying J coupling. But when we are talking about J coupling in NMR spectroscopy, this basically deals with, see, we all know that in NMR the only thing which we are measuring is the spin of the nucleus, okay? Nuclear spin. The nucleus are doing some spin, like they are going into a particular spin, and you are trying to basically perturb their spin, and that's what you are measuring in the instrument, right? Now J coupling basically talks about that how the spin of the groups which are near to a particular element affect the spin of that. So you can say it that J coupling is the indirect interaction of the of the nuclear spin or the nuclear spin magnetic moment or the nuclear spin moments along the bonds, okay? So it depends upon that how far the other species is. So let's say if you have a particular species, let's say you are taking proton NMR, and if this proton is attached to a particular group which is also NMR active, which does not have I equal to 0. So let's say we have a particular group, let's call this group as X. So if this group X has some I value, in that case the spin of this group X is going to affect the spin of proton, and that's why whatever NMR you are going to measure for this proton is going to have a little different effect than the hydrogen would have been separated from this X, okay? So it depends upon that what group is attached to it. Now this group over here is directly attached to it. There will be cases where the group will be little bit far. So that's what we are going to see. So J coupling take place by bond distance. So there are generally 1 J coupling, there is 2 J coupling, and there is 3 J coupling. In general, these three are what you are going to see. There are some exceptional cases also, but here you just have to look upon that there are 3 J couplings in major. 1 J coupling means coupling happening at a distance of one bond away, right? So it will be one bond away from the species, just like this was here. Then here 2 J coupling means distance of basically 2 bond away, right? Something 2 bonds away from the species. Then you can have something which is at the distance of 3 bond away. So that's how we see how they are going to cause coupling to this particular species, right? And this coupling is going to result in what? This is going to result in splitting of peak. This is going to result in splitting of peak. And how this splitting is going to take place, we already have studied it in the previous video. The formula which we use is 2Ni plus 1, where this I will depend upon this group X. I have written X here because I have mentioned with group X. So whatever group is over here, the I value of that group is going to cause splitting into that. So let's take an example and let's try to understand with that. So let's take an example of this particular molecule. It's a complex of manganese. It's HMnCO5. So if I draw this molecule roughly, so this is a octahedral molecule in which hydrogen I can make at any place. Let's put it on the axial position, and then we will be having these 5 carbonyl ligands attached to it, right? So we have these 5 CO groups attached to this. So now we have to understand that how the splitting is happening, and we are measuring proton NMR. Okay, 1H NMR is what we are measuring here, right? So now you have to see that this is the hydrogen which you are actually looking upon. This hydrogen is attached to manganese. There are other groups also which are attached, like carbonyl is there, in which carbon and oxygen are there. Generally carbon 12 is NMR inactive, oxygen is also NMR inactive. So NMR inactive species is not going to do anything. But manganese is NMR active. The I value for manganese is 5/2. Now we like these values will be given to you in the question, or you can, like, at the end of this video I'll give you a list of all the known metals and their I values. Okay, so the list will be there. You can pause the video and you can take a screenshot of that. But for now I am just telling you that the I value of manganese is 5/2. Now this proton, if there would be nothing over here, this proton would have simply given you a singlet because there is nothing attached to it. But now since manganese is there, so here is happening 1J coupling, and because of that 1J coupling, this manganese is going to split it up. The peak is going to split up. In how many lines this peak is going to split? So formula is 2Ni plus 1, where I we are going to put for manganese here, right? So if I put it, so 2N, how many manganese are there? There is just one manganese. I value of manganese is 5/2 and plus 1. So if I calculate it, so I will get 6. So this is going to give me 6 lines. So this particular single peak is going to split up into 6 lines. Okay, 5 and 6. So these are going to be 6 lines, and these 6 lines are called as sextet, right? So that's what you are going to observe for this particular molecule. Let's take one more example and see it quickly. Alright, so now let's see this particular molecule. We have HCO5. So this molecule is going to be square pyramidal in shape. Quickly draw this molecule, okay, and tell me that how many lines you are going to expect in this particular molecule. Okay, I am giving you I value of cobalt. So I value of cobalt is 7/2. Use this use this information to find out the total number of lines in this particular complex, and tell me in the comment section what answer you have got. Okay, now let's come back to the thing and let's see that like this is 1J coupling. Let's look upon the other J coupling which we can observe. All right, let's look upon this example. Now here I am going to explain you that how coupling takes place when the species is more than one bond away, and how the overall thing you are going to see. So the complex is HRH PME2O whole 4Cl. Okay, this is the octahedral species. Let me quickly draw this. So we will be having hydrogen over here, we are having chlorine over here, then we have these groups over here, right? So we have this OPME2, and this is everywhere, OPME2, right? OPME2. All right, so this is our species, or this is the complex which we have. We are looking at this hydrogen which is attached to the metal center. I will talk you about these things in the chemical shift video when I will discuss you about the chemical shift. There I will explain you that how exactly you are looking upon only a particular hydrogen which is attached to metal. So these basically, just in general, just understand that the hydrogen which is attached to directly to the metal is going to have negative chemical shift. So we are looking in the negative chemical shift value. So many of you might get confused ki why methyl hydrogen we are not looking upon. So these will give you in the positive direct or positive side of the chemical shift. We are just talking about the negative chemical shift value. Okay, and we will see how many splitting this is going to take place. So now this hydrogen, first of all, okay, let me tell you that what are the NMR active elements over here. NMR active nuclei which are here in the molecule. So the first one is of course hydrogen, because you are measuring proton NMR. So that's why I have highlighted it, that what you are measuring and what you are looking into. Second thing is we are going to talk about the other NMR active group, that is RH. Okay, so RH rhodium is also NMR active, and the third group which is NMR active is phosphorus. Okay, oxygen is NMR inactive, chloride is NMR inactive, and these methyl groups, in these methyl groups carbon is NMR inactive, hydrogens are there, but let's look upon it. So here we will be having so we will have phosphorus. All right, so we have all these groups which are NMR active. Let me quickly write down the I values. So the hydrogen has I value half, we all know it, but that is not going to make any difference because it's not going to split on its own, right? But still, let me write down that I value of hydrogen is 1/2, I value of rhodium is also 1/2, and I value of phosphorus is also 1/2. Okay, so that's what we all know. Now, which one group is nearest to it? So the nearest group is RH. In that case, the coupling says that the group which is nearest to the NMR group, or whatever NMR you are looking upon, so the group which is nearest to it is going to cause first splitting. So this RH is going to cause splitting for the first time. So that means this hydrogen was coming as a singlet, but this RH is now going to split it. In how many lines this RH is going to split? Let me do it here itself. So we have formula 2Ni plus 1. Since we have just one RH, so this will be 2 into 1 into half and plus 1. So if you solve this up, you will get 2. So that means the rhodium is going to split it up into 2 lines. So we are going to get these 2 lines over here. All right. Now, the next thing is that these lines are further going to split because of phosphorus. Now, how many phosphorus do we have? We have 1, 2, 3, 4 phosphorus. And now let's see whether this phosphorus is capable of causing splitting or not. So let's count the bonds, like how much bond away this phosphorus is. So if you see from this hydrogen, this is one bond from here to rhodium, then from rhodium to oxygen it's the second bond, and from oxygen to phosphorus this is the third bond. So these phosphorus are 3 bond away, and I told you that J coupling takes place up to 3 bond away, right? This is called 3J coupling. So what has happened with rhodium? It has caused 1J coupling, and phosphorus is going to cause 3J coupling. Now how many phosphorus do I have in the molecule? I have 1, 2, 3 and 4 phosphorus. And if I have 4 phosphorus, all these 4 phosphorus are actually equivalent to each other. Why they are equivalent to each other? Because you can see that they all are in same chemical environment. They all are cis to this hydrogen and they all are cis to this chlorine, right? So the chemical environment is same. I have discussed about the chemical environment in the previous video. In case if you have not watched, please watch it again. So phosphorus, all the phosphorus are same. I value is half. So how many splitting lines we are going to expect? So 2 into, how many phosphorus are there? 4. So that's why 2 into 4 into I value of phosphorus is half and plus 1. So if I solve this up, so I will get 5 lines. So that means each of these line is going to split up into 5 lines because of the phosphorus. So let us split it up. So we will have 1, 2, 3, 4 and 5 lines. 1, 2, 3, 4 and 5 lines. Okay, so that's how the splitting takes place. Now there will be the intensity also we can calculate of these lines, but that I will discuss in the next video. Okay, the next part of the video we will discuss that how you can find out the intensity of the peak. That is the next thing, but here we will just talk about that how splitting is taking place, because this, if you understand this, the next thing is very easy to do. So I think this is clear to you that how the group has done. So this single line was coming because of the hydrogen itself. These two splitting has happened because of rhodium, and further splitting has taken place because of phosphorus. Now the question should come up in your mind that what about these methyl group? Are they not going to cause splitting to this hydrogen? So let's look upon it. So if you see this particular hydrogen, and if I again draw this, so this hydrogen is attached to rhodium, and this rhodium was attached to, let's say, oxygen. This oxygen is attached to phosphorus, and it is attached to methyl group CH3. I am not going to draw the other methyl group, or let us put it Me. Now let me look upon that how much far these two hydrogen are from each other. So this hydrogen which we are looking upon, let's count the bonds from here. So this is 1 bond, 2 bond, 3 bond, 4 bond, and this hydrogen is actually 5 bond away. So they are 5 bond away from this, and I told you that the coupling does not take place generally beyond 3 bond. Okay, so beyond 3 bond you won't going to experience any splitting. So that's why these hydrogens are incapable of causing splitting to this. Although they are NMR active, if they would have been closer, they would have caused splitting to this hydrogen. But since they are so much far, they cannot do that. Alright. So this hydrogen is not capable of causing splitting. Whether these hydrogens are going to show a signal in the NMR, of course they will show. But here we are just looking upon that hydrogen which is attached to metal. And I initially also I told you that this will give you a negative chemical shift. So I'm looking upon the negative chemical shift group. All right. So I just made this example to make you explain about 1J coupling and 3J coupling and how you get total lines. So total lines will be 10 lines in this particular case. Let's try some more examples and let's try to understand that how this coupling takes place. Okay, so let's have an example of bridging groups. So let's say I have carbonyl which is attached to metal groups, and these are two metal groups, and it's a bridging carbonyl, of course. So this bridging carbonyl is going to cause a splitting, and it is going to split because of both these metal. Okay, so the number of metal which are going to cause a splitting will be 2 in this case. Let's see some more examples and see how this splitting is going to cause in other species. Like we have just done a proton NMR, let's see some other NMR as well. So let's take an example of a complex of rhodium in which we have bridging carbonyl. Okay, so let's take that we have eta 5 Cp, we have eta 5 Cp, and we have RH, and we have a CO, and we have whole thrice of this. Okay, so this is the complex which is given to you. So if you draw this, basically in this you will find out that there are 3 metal bonds. So you are going to get the 3 metals attached to each other like this, and you are going to have Cp attached to each of these metal cyclopentadienyl rings, right? So they are attached to them, and let's say that this carbonyl is labeled carbonyl. Okay, that is 13C. So we have 13C attached to, and that is a bridging carbonyl, by the way. Okay, so we have a bridging carbonyl. So all these carbonyls are bridging ones. That's why I am going to just make a star just to highlight it. So first thing is to find out that how many types of and by the way, we are doing 13C NMR over here. Okay, so here we are doing 13C NMR. So what is the NMR active species, or which group you are going to see for NMR over here? So you are going to look upon the carbon. Okay, so 13C NMR. You are going to look for the carbons. And are these carbon, the labeled carbons, are these carbon equivalent? So yes, they are all equivalent. If you find out, they all are in the same chemical environment, so they are all equivalent. How many types of carbonyl you have? The next question. So types of this 13C, or let me write down how many types of 13C I have. So basically I have just one type of 13C. All the 13C are actually of same type, right? So that means I will just get one signal if I just talk about 13C, but that's where your coupling comes into play. So you will find out that here each carbonyl is, or each carbon of this carbonyl is attached to 2 metals, right? 2 metal centers. And you know other species are NMR inactive, this oxygen is NMR inactive and all. So what is going to happen now? You will find out that this carbon is going to split because of these rhodium, and in how many lines it is going to split it up. So the splitting is going to cause because of rhodium, and the number of peaks in which it is going to split is going to be calculated by 2Ni plus 1. Now I value I am going to write down for rhodium. So initially a single line of this carbonyl, or this carbon was coming, not carbonyl, this labeled carbon, a single line was coming because the carbon is of same type, so it's not going to split its own self. Who is going to split it up? Rhodium, because of 1J coupling, and I value of rhodium I already told you is half. How many rhodium is attached to each carbonyl? So there are 2 rhodiums attached to it. So I will write down 2 into 2 into half and plus 1, and if you do it, so you will find out that you get a triplet. Okay, you get a triplet. So this line is going to split up into 3 lines. Okay, so in that case you can find out, or you can expect that the carbonyl is bridging carbonyl. Now let's assume that this is not a bridging carbonyl. Actually the molecule is not bridging, and it's a normal molecule in which carbonyl is just attached as a terminal carbonyl, not as the bridging ones. So let's assume that the carbonyl is not bridging, but it is a terminal carbonyl. So in that case I will be having the same molecule, but the structure will be like this. Okay, 3 metal bonds I have made, 3 Cp we have, and 3 CO. Again, if you see all the all these carbonyls are of labeled ones. Okay, all these carbonyls are of labeled ones. Now you will see that all of them are equivalent because their chemical environment is same, but in how many lines now they are going to split up? So who is going to split them up? The one metal is going to split them up, and the single line which was coming because of this labeled carbon is going to split up in how many lines? So I am going to use 2Ni plus 1. Your N value is 1 because there is just one metal attached to this. I value is half and plus 1. So if you see, you are just going to get 2, that is a doublet. So that means this single line which was coming because of 13C is now splitting up because of rhodium into 2 lines. So that's how you can differentiate if you have a solution, and if you have molecular formula and you want to find out that whether the carbonyl is bridging or the carbonyl is terminal. So in case of terminal carbonyl, we got doublet as the peak, whereas in case of bridging carbonyl we got triplet as the peak. So this is how NMR helps you to find out different type of isomers in the case of inorganic NMR spectroscopy. Let me take few more examples to give you more application of it. So now let's take one more example. We have, let's say, P4S3 as the molecule. If I draw the structure of this, and we are doing, by the way, 31P NMR in this. Okay, so now we will look for phosphorus here. So let me draw the structure of this. So we will have phosphorus attached to sulfur, then phosphorus, then it is attached to sulfur, and then attached to phosphorus over here, and here again sulfur and then phosphorus. This phosphorus and this phosphorus are attached without any sulfur in between them. So let me make this bond a little bit sharper. So phosphorus, let us attach both of them like this, and they are attached to this phosphorus also like this, right? Something like that. Now in this species, first thing is to find out how many types of phosphorus you have, because you can see all phosphorus are not equivalent to each other. So you will see that basically you have a So basically you will find out that there are two types of phosphorus. Phosphorus of type A, which is actually attached to 3 sulfurs in such a way, whereas these phosphorus which are attached to sulfur and 2 other phosphorus. So this is phosphorus of type B. Now this phosphorus is also of type B because it is attached to 2 phosphorus and 1 sulfur. So this is also of type B, and this phosphorus is also of type B because it is attached to 1 sulfur and 2 phosphorus. So we have 2 types of phosphorus. So that's why there will be 2 types of peak, or 2 signals is what you can expect in this. So you can expect 2 signals in this. Now what about the signal of phosphorus of type A? Okay, so let's do it one by one. So for phosphorus of type A, see, who is going to split this phosphorus? There is no like sulfur is not NMR active, so sulfur is not going to split it up, of course. The other phosphorus which are over here, which basically are different type or of different chemical environment, that's why they will cause splitting, and that's why the number of splitting which you are going to see in this case will be of 2Ni Pb. Why Pb? Because this is phosphorus of type B, not lead. Okay, Pb plus 1. So you are going to have 2 into how many phosphorus of type B are there? So 3 of them. I value of phosphorus is half and plus 1. If you calculate it, so you will get a quartet. You are going to get 4 peaks or quartet. So phosphorus of type A is going to split up into 4 lines. Okay, into 4 lines it is going to split up. Whereas if I talk about phosphorus of type B, let's talk about that now. If I talk about phosphorus of type B, so all phosphorus of type B are equivalent, so they will not split each other. Who will split them? Phosphorus of type A will split them. Okay, so we will have splitting in this form, 2Ni Pa plus 1. Now Pa is phosphorus of type A. How many phosphorus of type A are there? There is just one of them. I value is half and plus 1. If I solve this, I will get 2 or doublet. What I can say is a single line coming from the phosphorus of type B is going to split up into 2 lines with the help of phosphorus of type A. So phosphorus of type A is going to show you a quartet, and phosphorus of type B is going to show you a doublet. So that's how we find out, or in the overall spectrum you will get a doublet and a quartet. That's how we find out the splitting, and that's how we tell how many lines or how many splitting is going to be there. Okay, before going further, just make some note of it, that if you have two groups at the same distance, and if some group is cis, okay, and some group is trans, so in that case trans group will have more coupling as compared to cis. So J trans is always greater than J cis. So cis coupling is less observed compared to trans coupling. That's because of the orientation of the bond in the same direction. In the same way, this is the first note which you have to make. The second thing is that if the groups are axial and equatorial, in that case J axial has more coupling. Okay, so axial group couple more than J equatorial. So these things will come up in the case where there is no fluxionality, the molecule is rigid. In that case, the axial splitting is going to be more compared to equatorial splitting. Let me give you an example of that. Let's say we have this molecule PF4NCH3 whole twice. Let's make this molecule, and here I have to calculate 31p NMR of that. Okay, so this is very important, that what NMR you are looking upon. So we will focus on phosphorus over here. The structure will be, of course, trigonal bipyramidal kind of geometry, and the shape will be like this. We will have phosphorus, we will have fluorine, 2 fluorine over here like this, we will have 2 fluorine over here like this, and nitrogen over here like this, and 2 CH3 will be like this, CH3 and CH3. Okay, now if you see, these fluorine are axial fluorine, these are equatorial fluorine. Let's assume that nitrogen over here is like 14N, which has I value of 1. Fluorine has I value half. So let me write down NMR active molecule here, or NMR active nuclei over here. So we have fluorine which has I value of half. We have nitrogen apart from phosphorus, because phosphorus is what we are looking upon. So it will not cause a splitting on its own. So we are just looking upon the other things. Nitrogen has I value of 1. All right. And we also have hydrogen here. So let's look upon them also. I value is half. Let's see how many lines it is going to split up into. We have two types of phosphorus. As I said, one will be axial and one will be equatorial. So who is going to split it up first? So these axial fluorine are going to split it up first. In how many lines? So I'll just draw it here. Okay, so this was a single line which was coming from the phosphorus. Okay, this is from 31p, that's coming straight. Nobody is there to split it up, but now fluorine, axial fluorine are going to split it. In how many lines? 2NIF plus 1, and that's going to make it like 2 into half and plus 1. Now you will have so now you will see that you will get a triplet. So these are going to split it up into a triplet. That means it's going to split it up into 3 lines. All right, now next we have nitrogen and we have fluorine at the same distance. Now when you have two groups at the same distance, who is going to cause more splitting? That should be done according to the J values, and they have certain J values and they will generally give you an exam. But for now we are assuming that JPF is greater than JPN. That means the coupling with phosphorus and fluorine is more as compared to coupling between phosphorus and nitrogen. So since this coupling is more, so next splitting who is going to do? These equatorial phosphorus again, equatorial fluorine. Again they are going to split it up into 3 lines. So these peaks are going to split it up into 3 lines again. Okay, so 3 lines it is going to split up, and at the end what will happen? That this nitrogen is going to split it up. So I'll just write down here. So this is splitting, the first splitting has happened because of axial fluorine. Okay, this splitting which has happened is because of equatorial. All right, so at the end, so this splitting is because of 31p. This thing which you are observing here is because of axial fluorine. This is because of equatorial fluorine, and at the end these nitrogen are going to split again into 3 lines, and that's what you are going to see. Now don't look at the intensity of the peak, because that thing I will discuss in the next video. So that's the concept for the next video. So total number of lines which you are going to see is 1 2 3 9 and 3 set of 9. So you will get total 27 lines in the spectrum of this. All right, so let's take a question at the end which was asked in CSIR NET exam. It was based upon same coupling concept, and let's see how to do this question. So it says, assuming a JPH greater than JPB means more coupling between phosphorus and hydrogen compared to phosphorus and boron. The expected 31p NMR spectrum of H3P11 BCl3 for B having I value, boron is having I value of 3/2. So first of all, we have to make the molecule. Okay. So I think similar question we have done in the previous video, but let's do this. So BCl3 will be a planar molecule. So let me make it planar. So these three groups are plane. Okay, they are on the same plane. So let me erase these lines. Okay, so they are on the same plane. This shows, this dotted things shows that they are on the same plane. And we have pH3, which is going to be pyramidal in shape, right? So we will have pyramidal shape like this. Now this phosphorus has excess of electron, boron, BCl3 is a Lewis acid group, so it is going to accept electron. This is the molecule which we are going to have. Now what you have to see is we are doing 31p NMR, right? That's what we are doing here. So who is going to split first, or who is going to cause splitting first? Because JPH is more, so these hydrogen are going to cause splitting first. Okay, so they are going to cause splitting first. Now in how many lines they are causing splitting? So let's do that. So we will have 2Ni plus 1, that's the formula to do it, and I am doing for hydrogen. So it will be, how many hydrogen are there? 3 of them. So 2 into 3 into half and plus 1. If you solve this up, you will get 4 lines. Okay, so that means that a single line coming from phosphorus is going to split up into 4 lines because of the hydrogens. Now what will be the intensity of these 4 lines? You all know it is going to follow the Pascal rule, although I'll explain this in the next video in detail. But for now, just understand that the splitting ratio will be according to the Pascal rule, and that will be 1:2, 2:2, 2:1. Okay, that's going to be the intensity of the peak. So initially this cannot be like, they have to be 4 line, they cannot be 2 splitting. So option A and option B you can just cancel out. Among option C and D there is something. Now who is going to cause splitting further? So boron is going to cause further splitting to it. And how many lines boron is going to cause splitting? So 2Nib plus 1. Use this formula for that. So that will be 2 into just 1, and boron is 3/2 and plus 1. Solve this up and you will get 4 lines again. But right now these 4 lines are not going to follow Pascal rule. Pascal rule is followed by those which have I value half. I will discuss this in the next video. Okay, so for now just imagine that these lines are going to split up into 4 lines, and since they are not going to follow the Pascal rule, so their ratio is not going to be 1:2:2:1, but their ratio will be 1:1:1:1:1. So they all 4 lines will be of same intensity, which is shown in option number C. So if you look upon option number C, let me zoom this up a little bit for you. So now you can see on the screen how option B, how option C and D are different from each other. In option C, all the 4 lines are of same intensity. In option D, you will find out that the line in the central lines are of more intensity. So this is following the ratio 1:2, 2:2, 2:1, but this is following 1:1, 1:1, 1:1. So the overall intensity of these peak, is going to follow option number C. How the overall intensity will come? Of course, the first peak will be smaller, the central 2 peaks will be bigger, which are over here, and the terminal 2 peaks are smaller, and the final peaks are like 1:1:1:1 intensity, and the major peaks is of 1:2:2:1. So I guess you understood this. In case if there is a doubt in this particular thing, or if you have not understood it, stay tuned for the next video. In the next video I will explain you how splitting happens, how how the concept of multiplicity, how the concept of coupling and the Pascal rule in together is going to cause the intensity of the peak. So how you define the intensity of the peak. So stay tuned for that video. In that I'll explain you in detail. Alright, so I'll keep this video till here. So I hope whatever we discussed in this video is clear to you. You have understood it well. And in the next video we will further discuss about the intensity part, and in the upcoming videos we'll talk about chemical shift. We will also talk about that how you find out splitting or chemical shift of certain specific groups which show fluxionality. Okay, so those things are part of the future videos. For now I'll just sign off from here, so stay tuned for the next part. Till then, have a great day. Bye bye, take care. Hey guys, so I teach live on Unacademy Plus platform. Here I teach for the CSIR UGC NET category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Unacademy Plus subscription. So do make sure that you take the Unacademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there, and the classes are quite regular over there. So make sure that you take Unacademy Plus subscription by using my referral code, that is N_Huda. That's it for this. Thank you so much.